Okay, so good morning, everyone. A very warm welcome to today's session on advanced nonlinear contact and joint modeling in Ansys Mechanical. This session will deep dive into the principles of nonlinear contact mechanics, joint behavior, and advanced simulation techniques to enhance product durability, performance, and reliability. To give us more insights into this topic, we have our speaker for the day, Mr. Chetan Patel, who's the application engineer, Ansys Mechanical at ARK Info Solutions Private Limited. So he specializes in CAE, FEA, and CFD simulation and holds a degree in aerospace engineering from MIT ADT School of Engineering, Pune. With expertise across finite element analysis, multibody dynamics, and CFD, Mr. Patel has conducted over 50 technical training sessions, FDPs, and STTPs, providing project consultation and technical support to both academia and industry. So join us as he shares his knowledge and demonstrates how effectively set up and interpret complex contact and joint simulation using Ansys Mechanical. Good morning to you, Chetan, and good morning, participants.
Yeah, good morning all. Thank you, ma'am, for a warm introduction. So this today's session will be like deep diving into the topic on nonlinear contact modeling and joint modelings using the Ansys Mechanical. So those who are already been familiar or either those who have already attended my previous webinars, so those were totally based on the topics related to the particular linear, non-linear analysis and all. So this particular topic is dedicated for just non-linear contact simulations and joint modelings. So basically how the particular contact is created and how those are like whatever the kind of types of contacts are available with us. So how those are categorized into linear and non-linear contact types and what is their particular behavior. So all those things we are like going to see in this particular session. So we'll have even two more demonstrations on both the things like contacts as well and on the joint as well. So today's agenda for this particular topic will be a short introduction to the nonlinear analysis, then the type of nonlinearities those are available from which we will be focusing on the contact nonlinearity. Then we will have an just a short overview about how the contact and joint modeling is done in Ansys Mechanical through the slides itself. Then we'll go on the Ansys Workbench and Ansys Mechanical interface to set up the nonlinear contacts and joint simulations for different kind of models. So as I did mention earlier, so this there will be two different kind of workshop that we will be performing over here. So the first will be a snapfit model for contact simulation where we'll see how the particular type of contact, if we are using linear and non-linear types, then how the particular simulation results get changed. We'll look out into the post-processing and analysis part as well. Then after that, the second webinar will be dependent on the excavator arm kinematic simulation. So where we'll be using the joints for this particular simulation. So whenever we want to perform kinematic dynamic simulation, we usually go for the joints. But how these joints will be useful and when we should use this particular joint, how to model the joint. So we'll look into those kind of things in more detail. So the first thing that we are going to see over here is what is a particular nonlinear behavior. So nonlinear behavior does usually occurs whenever there is a particular change in the stiffness due to the load that we are applying on the geometry. So there might be several different kind of loading conditions, various different kind of loading conditions are there. Under those different kind of conditions, if the stiffness of the particular model that we are using, so if it does gets changed, then particularly your model can be considered as a non-linear kind of structure, or either the behavior of the model is considered to be a non-linear kind of behavior. So this particular stiffness change is categorized into three different parts, like when we can see the particular changes in the stiffness of the model. So those are parameterized into three different categories over here. So the first one is the material dependency. So basically due to the material properties that we're using for the model, so that might affect to change in the stiffness of the geometry due to the particular loading condition. So everything does changes with respect to the loading itself. So the first thing is the materials that we will be using. The second is about the particular geometric deformations. So as you can see over here, the first one, first image that has been mentioned over here. So that does defines how the particular body's elastic limits get changed from elasticity to plasticity, that significant changes in the stiffnesses does particularly changes the behavior of the model from linear to non-linear. The second image does represents the last deflections in the body. That does represents the second type of non-linearity, which we consider to be the geometric non-linearity. And the third type is the change in the contact status. So whenever you are considering there might be multiple bodies, those are in contact with each other. So there will be always a contact that which we will be generating between the bodies. So that particular contact, if it is linear or non-linear, so what kind of behavior the linear and non-linear kind of contacts might create. So those kind of change in the stiffness due to the contacts also might affect your particular simulation to get converted to a non-linear behavior. So we'll look out into the third type, that is the change in the status due to the particular contacts. So these types of non-linearities are there and how those are particularly turned on. So whenever we are going for geometric non-linearity, we usually know that last deflection is the only thing that affects geometry to undergo non-linearity. So basically we turn on the last deflection over here. So whenever we turn on the last deflection, the first type of non-linearity, or either you can consider there is no particular sequence of non-linearities to occur in a geometry. So you can consider anything to be the first. So over here, in our particular sequence, so geometry has been mentioned. So in this particular thing, last deflection, if you are turning on, then the particular non-linear simulation will get turned on in your particular overall simulation. Then the second type is your material non-linearity. So material non-linearity does totally depends on the properties that you are using to define a material. So if it is a linear material, or either the properties that you have defined to the body to be only linear, not consisting any non-linear properties into them, so then the particular simulation will also be considered as a linear kind of simulation if you are using that particular material for the geometry to be defined with. Or if you are using some non-linear properties for the material like hyperelastic properties, plasticity, creep, or either any viscoelastic properties and all. So all these properties might affect your particular simulation to get converted from linear to non-linear. So this was the second type. The third type that we are going to focus on over here is the contact non-linearity. So basically what kind of contacts are available, the type of contacts those are available. Whenever we create contact between the geometries, either it might be automatic, either it might be manual contact. So at the initial, by default, it will always create bonded kind of contacts. So there are different kind of contact types, those are available, like bonded, no separation, as you can see in this image over here. So bonded, no separation, frictionless, rough, frictional. So these are the type of contacts which are available. So if you are creating bonded kind of contact type, then it will be considered to be the linear, no separation are as well considered to be the linear itself. But the remaining three are considered to be the non-linear kind of contact type. So it does totally depends on you based on your particular selection of the type of the contact. The particular simulation will get converted to a linear or either non-linear simulation. So whenever we are including some kind of particular non-linearities in a model or in a particular geometry, so it does affects the particular convergences as well. So whenever we are solving with non-linear model, so usually the result doesn't take much amount of complexity, doesn't consist of much complexity into it. It easily gets converged with it. So when we try to include the first type of non-linearity, either it might be anything, geometry, material, or contact, whatever it might be, but it will increase your particular chances of occurring the divergence. So divergence occurs whenever there will be some kind of non-linearity that will be included in the model. So when you are including all the three type of non-linearities at a single time, then there are higher chances of divergence to occur in your particular model. And if the divergence does occurs in your particular model, then how to analyze your particular simulation and how to find out or figure out the results related to your simulation, you will also figure out about that particular thing. So when it comes to divergence, on which particular results you should be focused on is mentioned over here. In case of non-convergence, that is divergence, analyze the last converged substep. So basically, we will see how to analyze these kind of results as well. So it might occur due to any kind of non-linearity, not just due to the contact, but with respect to any kind of non-linearity, it might occur. So if it is occurring with respect to the contact non-linearity, how we will be particularly recognizing it, and how we will try to overcome that particular divergence that is being occurred in the non-linear simulation. Then the next thing that usually you should know about the non-linear simulation is what kind of process is being followed for solving a non-linear simulation if we compare it with the linear simulation. So how does the particular mechanical solver does behave when the stiffness of the model does keeps on changing? So in that particular simulation in a non-linear analysis, so you can see the response cannot be predicted directly with a linear equation set. So whenever we are using a particular stiffness matrix equation, so that's only made for the particular linear set of equations. So through using that particular set of equation, we can't solve this like change in the stiffnesses of the model. We can't solve the particular non-linear behavior of the material or either non-linear behavior of the model. So basically to overcome this kind of thing itself, the nonlinear structure or the nonlinear analysis does uses a iterative series, which is also called as a Newton-Raphson method, which uses the linear approximation method to get the particular simulation corrected in more sequential and more uniform way. So how this process is done, how the particular mechanical uses this iterative process, and how we are going to recognize this, how we are going to figure out how the convergence is going to occur with respect to the iterative process. So we'll try to figure out those kind of things as well over here. So this Newton-Raphson process we'll discuss in more detail in the like demonstration at the time of demonstration itself. So this is about the contact, like what all things you should know before you begin with the particular contacts and all. How the particular contacts are bifurcated into linear and non-linear kind of contact types. So as you can see over here, when you're going with respect to the contact types, so we have 5 different kind of contact types which are mentioned over here. That is bonded, no separation, frictionless, rough and frictional. So these kind of contact types are available. In front of it, the number of iterations are mentioned over there. So when it comes to particularly solving a linear simulation, there are no multiple iterations those are performed. So if there is just a single iteration that is required to solve your particular simulation, that means there is no particular change in the stiffnesses due to the particular like uh, kind of conditions that you have applied in your simulation. So that will be considered as a linear kind of simulation. So bonded and no separation are considered to be solved with only one number of equation. The reason behind solving it with only one number of iteration is there is no particular gap and sliding that is allowed in bonded, and basically no separation as well. There is no gap in the body. So when both the bodies doesn't allow gap between them, so whenever there are multiple bodies, those are in contact with each other. So if both the bodies doesn't allow any kind of separation between them, that means bodies can't get separated from each other even if you apply whatever amount of force that you want to apply on it. So in that situation, the body behaves like a stitched body, that is a single kind of body itself. So in that particular situations, the stiffness in the body doesn't get changed a lot. So that particular thing can be analyzed with respect to linear kind of simulations itself. So that's why this particular two type of contacts are considered to be the linear kind of contact type. In this remaining three kind of contact type, that is frictionless, rough and frictional, basically gaps are allowed. So if gap is allowed, that means the body can separate from each other. Now both the bodies have different kind of stiffnesses with respect to their body configuration, specifications and material properties. So if that is the situation over here, under those kind of situation, the particular simulation will get converted to multiple number of iterations, which will further result into non-linear kind of contact type. And whatever the kind of contact types those are available, so you can see their particular behaviors over there. So bonded doesn't allow separation and sliding on the particular geometry. No separation doesn't allow separation over here, that means there should be no gap between the bodies. And even sliding is not over here. For no separation, sliding is allowed. So that means no separation can only slide over each other, the bodies can slide over each other but can't get separated from each other. So there are many applications where you can even go with the no separation kind of thing. So after that, we have frictionless, where the bodies can get separated and even they can slide over each other. Then rough is there, where particular bodies can get separated from each other, but due to the roughness that you are defining between the two bodies can't slide over each other. Then the third one is the frictional. So basically, frictional does allows you to get separated from each other and even to slide over each other, but there will be a particular resisting force, that is your particular frictional force that will be acting in this particular contact. So that will try to resist the sliding that is being happen in the particular two different type of bodies. So whenever you are creating any kind of contacts, those are mentioned over here in this list. So you need to also do the technical verifications. Technical verifications in the sense like, you need to analyze whether whatever the kind of contact type that you are using for the simulation, whether those are considerable for the simulation or not, whether you can use those particular simulation, uh, for use those kind of contacts for the particular simulation, whether it will work for your particular simulation or not. It will give you an idea at the initial itself before you go for the solve. So how that particular technical verification is done, that is done using the contact tool which is present over here, with respect to the initial information about contacts and the real constants. So basically, whenever you will import a contact tool over here on your particular contacts that you have created, it will give you such kind of table where you can see the particular contact regions might be highlighted into different kind of colors like gray, white, red, and orange. So all this particular color band does defines whether the particular contact that you have created can be used for the simulation or can't be used for the simulation. This particular thing will mention you those kind of results over here. So if it shows you red color, then you can't use your particular contact for the simulation. It will obviously give you some kind of errors over there. So in those kind of situation itself, you need to change the particular contact type, or either you need to make some kind of modifications with the contact. So we'll look out into those kind of things as well, how we can use the contact tool to particularly recognize some irregularities in the contacts and try to fix those kind of things as well over here. Then in the solution information, to plot the Newton-Raphson residual, that is, you want to particularly analyze how does the model does behaves with respect to the change in the contact stiffness, or either due to the change in the particular non-linear behavior. So under those kind of conditions itself, you will have such options like force convergence, displacement convergence, and all other convergence graphs over here. So we'll try to recognize how these particular things are analyzed and how to read the particular graph that we are getting from the particular simulation. So even in the solver output, you will have the details about the particular iterations those are being performed using the Newton-Raphson method. So we'll discuss about those things as well when it will come to the contact. Now about the joints. So basically, joints are usually created in the similar way as we create the contacts. So there are two methods of creating the joint as well. That is an automatic method and a manual method. So we'll look out into those kind of things as well. So joints are usually used to provide kinematic motion to the body. So when it comes to particular kinematic simulation, we either use contacts or joint, but joints are mostly preferred when it comes to kinematic simulation. But even if there is a particular chance of inclusion of rigid bodies in the simulation, so to give motion to the rigid bodies, the only method that is available is the joints over here. So we'll look out into that particular simulation as well, how we can use the joints to particularly perform the kinematic simulation, how the joints are modeled. So we'll look out into those things. Then joints are represented by their own coordinate systems. So we'll discuss about these things like whenever we try to create a particular joint. So how does the joints provide motion to the geometries? So if we are considering some of the bodies to be rigid or either some of the bodies to be flexible, it will be considered to be a particular multi-body dynamic simulation. So if we are performing multi-body dynamic simulation, then particularly you will make use of rigid bodies and flexible bodies. So even those bodies might have their own coordinate system, but whatever joint that you will create, the joint will also has its own coordinate system. So how to work with respect to that coordinate system as well, we'll find out and figure out those particular things. So we'll go into connections as well. When we'll try to create the joint, we'll discuss about these things in more detail. Then whenever we are using the joints, so basically to provide motion to your particular geometry or the model that you have with you, so you can use the particular joint conditions as well. Like you can apply the particular load on the geometry using the joint that you have created between the bodies. So that particular joint can be of various different types. So joints are as well of various different types, and due with respect to the particular types of the joints, you can provide the particular conditions as well. Like the particular, if you're using a translational joint, then you can apply force on the particular geometry, velocity, displacement, acceleration. If you're using revolute joint, then you can provide rotational velocity, rotational acceleration, moment. So all these things as it has been mentioned in the description. So you can see various different kind of things that you can apply with respect to the joint conditions as well. So joint load properties as well, we will discuss it into more detail. Then the most important thing that you should do whenever you are creating any kind of joint is the redundancy analysis. So basically whatever joint that you have created, whether that joint is under constraint or over constraint, to recognize those kind of thing, it is very much important to do the redundancy analysis. So basically if there are any kind of over constraint joints in your particular simulation, so the redundancy analysis can easily recognize which particular degrees of freedoms of your joints that you have created between the bodies might have some kind of irregularities into them, and to fix them as well. So there itself in the worksheet that you have for the redundancy, you can modify the particular joints that you have created. Then in a similar way, under constraint joints does also work in the similar pattern. So you can go for the redundancy analysis itself, where it will showcase you, and even you can set some kind of particular constraint to the joint that you have created. So under constraint and over constraint are two different things that you need to particularly recognize for your joints that you are trying to always create. So this particular overall webinar will be now showcased with like the topics that we are going to discuss related to the non-linear contacts and the non and the particular joints that we are going to use. So this particular demonstration will be divided into two number of workshops over here. So that particular workshop will consist of a snip fit model. So the thing that you can see on the left hand side of the screen, so such kind of model is available. So you can see the particular sliding between both the bodies, the deformation in the bodies, and whatever the particular bodies, those are in contact with each other. Either those are actually in contact with each other, what if they get separated from each other? So we'll look out into those kind of contacts, how to create such precise kind of contact between the bodies and how to provide such kind of motion to them. So we'll try to figure out those things. And the second workshop will be on your particular joint simulation. So how to create the joints on an excavator arm. So we will look out into those things, how to model the joints and all other things. So we'll just begin with the workshop then. Okay. So first of all, to perform the nonlinear contact simulation, I'll just create a static structural analysis system over here. In this particular static structural analysis system, we will be using a snippet model itself. So already I have a created snippet model over here. So that particular model is being divided into the same kind of pattern that was showcased in this screen over here. So the similar kind of model is available, but the actual representation of the model is something else. So we are just using a half part of it, so that particularly we don't have to perform the overall simulation on the overall geometry. Instead, we have divided that particular part into two halves over here. So I'll be using that particular part itself. So the geometry that I will be using, I'll just import that geometry over here. Okay. So I'll just showcase you what kind of geometry that I'll be using for this particular simulation. Before that, I'll just go to the engineering data so that like I'll modify some kind of material properties over here. The reason that I'm modifying this particular material properties, those are available over here for the structural steel material, is I don't want to waste much amount of time into getting the result for the simulation. If the body is too stiff and if the body doesn't undergo easy deformations, then it will take more amount of time and more amount of particular force requirement to and even I don't know what amount of force that might be required to displace the body in such a situation. So what I can do over here is I can just particularly delete some of the properties which are not required for my simulation over here. uh, I'll be using only the linear elastic properties itself, because whatever the particular behavior of the body is there, as you can see, both the bodies are undergoing some kind of deformations and then they are coming back to their original position. But the upper body is undergoing very higher amount of deformation, because deformation in the sense it is undergoing very higher amount of displacement in it. So that particular displacement we need to recognize it well, and to recognize and to consider that particular higher amount of deformation, we will be turning on the last deflection option over here. So this will be a particular inclusion of two different kind of non-linearities, that is geometric and contact non-linearity. But we will be more focused on the contact non-linearity, not on the geometric non-linearity. So that's why I'll be like deleting some of the material properties which are not required. Even if I would go to the geometry over here, I'll just showcase you what kind of geometry which is available with us. So that particular geometry is a 2D geometry which is available. So I won't be performing 3D simulations on the geometry, because I just have a 2D model with me. So whatever particular thickness is there, so I'll provide that particular thickness in the simulation itself. So it will consider the thickness and it will try to make my model behave in similar kind of way. So it's starting the space claim. Meanwhile, I'll just modify the properties which are available over here. So as you can see, the isotropic elasticity properties, which are usually the linear elasticity properties, where you can figure out the Young's modulus is a little bit high. With actually it's for the structural steel, so it might be high. So I'll try to reduce the particular Young's modulus of the material as well. And if I would increase the Poisson's ratio, then Poisson's ratio does particularly like defines your deformation in the model. So if I would increase the Poisson's ratio, there will be higher amount of deformation with lesser amount of force that I will be applying on the geometry. So the body can easily undergo deformations and the stiffness of the particular material will be reduced with respect to the Young's modulus itself. So I'll change those properties and I'll be using that particular material for the simulation so that even it doesn't affect the results for my simulation. Okay. So as you can see, this particular geometry is for this particular geometry is a 2D geometry which is available with me. And always whenever you are creating a 2D model or either you want to use your particular 2D model, so you should keep this thing in mind that you should always create your model on a XY plane itself. Because for 2D simulation, only the XY directions are available to provide the conditions. So that's why if you try to create your model on any another direction, your model won't be recognized by the solvers over there in Ansys Mechanical or either in any particular simulation software. So you should always create your 2D models on XY plane itself. So it has been created over here. There is a small amount of gap which is present between these two bodies over here. That means the bodies are already not in contact with each other. So whatever the conditions that we did saw for the different type of contacts that we do have with us, that is bonded, no separation. So these two types doesn't allow separation between the bodies, but the bodies are already been separated from each other. So that particular thing might as well affect the selection of the type. So if you would select bonded or either no separation, then it will be a particular irregularity between the geometries. We'll see how to particularly recognize this thing in contact tool. As I do already know, there is a gap between the geometry, but whether the simulation software does recognize it using the technical verification method. So we'll be looking into those things. So first of all, what I'll do over here is I'll just open the Ansys Mechanical. Before opening it, in the geometry, you can see there is a property tab which is present over here on the right hand side. In this particular tab, I have the analysis type to be changed from 3D to 2D over here. So when I'll change it to 3D from 3D to 2D, my third dimension will get like will be neglected basically. So whatever the deformations or motions or stresses in the third direction will be there, or with respect to the third direction will be there, those will be totally neglected over here, and only the particular planar motions, the planar deformation, planar stresses will be considered over here for the simulation, and only XY direction will be there to provide the particular conditions. So I'll now open the Ansys Mechanical over here. I'll just close this space claim as it's not required further. Okay, so geometry import has been successfully done over here. Okay. So basically this particular model's behavior, as I did already showcase to you in this particular PPT, which is available over here, you can see what kind of motion that I want to provide to the geometry, what kind of boundary conditions I need to provide to it. So I'll need to decide those things, but before that, I need to work on the contacts between the particular geometries over here. So first of all, I have the geometry which is available with me. So this particular geometry's 2D behavior can be defined at the initial itself before we proceed with the simulation, because 2D behavior itself will decide what kind of like behavior of your model will be there for the simulation. So as you can see, if I would click on the surfaces, that is these two surfaces which I have in the geometry over here. So their particular thickness, if you want to provide, then it can be only available with respect to the plane stress problem. If I would go with the axisymmetric does mention this particular model is just a particular cross-sectional dimension of your particular actual model. So we don't, this is not the actual condition over here. If I want to provide some amount of thickness, then plane stress is the only thing through which I can provide its thickness over here. I can decide what is the actual thickness of this particular model. If I would go for the plane strain problem, plane strain is a particular thing where the thickness of this particular geometry will be considered to be infinitely long. So that means whatever the stresses that will be generating on this particular planes, that means this particular surface and this particular surface, on the overall infinite length of the particular geometry, wherever you will take a cross section of the same kind of body, then there will be the same kind of stresses that will be generating. So that particular consideration will be applied over here using the plane strain problem. So if you would select the plane strain, you can't provide thicknesses to your geometry as it will be considered infinitely long over here. So there will be no particular thickness that will be defined for your particular whatever model that you have. So instead of this plane strain, we'll be using a plane stress problem where we can define the thickness to these geometries over here. So the default thickness that has been mentioned over here is somewhat 1000 mm, but the actual dimension of the model itself is not too high. So we can only provide it somewhat 5 mm of thickness. So if I'm providing 5 mm of thickness to one surface, the same amount of thickness to be provided to the second body, which is in contact with the first body. So if there is a situation when you want to provide thicknesses to the particular surface geometries, so if both the bodies are not in contact with each other, then you can provide different thicknesses to both the bodies. But if those are in contact with each other, then the thickness shouldn't vary for both the bodies. So that's the only situation. So both the bodies are in contact with each other. So we need to provide the similar kind of thickness to both the geometries over here. Then the next thing over here is the particular connections. Material has already been defined to this. That is the structural steel with whatever the properties those were available. So I'll just go over here. I need to change the properties of this particular material. So I'll mention 2.8 e raised to 9 to be the Young's modulus, a little bit reduced value, and 0.35 to be the Poisson's ratio, a little bit increased Poisson's ratio over here. So that deformation can be easily generated for the geometry. So I'll just refresh materials over here so that the material will have the similar kind of properties that I did mention, that is 2800 megapascals of Young's modulus and Poisson's ratio of 0.35. Once this is done, we have the connections that has been already been created over here. So these connections, that is the contact between the geometry, has been already created over here, a contact region. This contact region has been automatically generated due to this particular group which is present over here. So basically this contact group does always helps you in creating automatic contacts or either automatic joints between the bodies. So if you want to create automatic contacts, then you can just right click on the connections, right? Click on insert, and over here you can find out the connection group. In this connection group, you can create automatic contacts and joints as it is mentioned in the description over here for this connection group. So this particular thing can be used for creating automatic contacts, or either you can use the manual contact region as well. And in the similar way, we have beam joint option as well. So as of now it is not available for this 2D modelings over here for this particular geometry, but there will be a particular joint connection as well that we can provide between the bodies. So we'll discuss about it in the next workshop or the demonstration. So over here the contact has been already been created between the bodies. So as you can see, the contact which has been created between these two bodies is defined over here. Even though there is a gap between the geometry, you can see there is no actual connection between the bodies, but still there is a particular connection that has automatically been generated. This particular gap has been neglected by the automatic contact generator, that is this connection group. This is because there is a tolerance value that has been decided over here, which is of 0.14763. So mm. So basically this particular dimension, this particular tolerance value has been considered over here. So if both the bodies are between this particular value over here, then the automatic connection will be created between them. And this is the automatic connection which has been created between these two bodies over here. So the next thing that we need to do over here is the contact has automatically been selected, but whether this contact will be will be useful for a particular simulation, the type of contact which is available over here by default is the bonded kind of contact type. And bonded kind of contact type does defines there is no separation that is allowed between the bodies. That means bodies can't get separated from each other. And even if you would see this particular PPT that we have working in the background itself. So over here in this particular table, it has already been mentioned, there is no separation that is being allowed and no gaps are allowed between the bodies. But in this particular geometry, there is an actual gap which is present from the initial itself, from the simulation start itself. So basically, if this particular gap is available and if we are using a bonded kind of contact type, how does the model does behaves over here? Now this is an automatic generated contact. So it will still behave as a particular contact itself. There will be no like irregularity between the bodies. But actually the particular condition that we are trying to figure out for this particular two body, the particular behavior that we want between these two body can't be achieved over here. So the reason we can find out. So what I'll do is I'll just include a contact tool over here. This contact tool will be applied to this contact region. So I'll just rename based on definition. So this is a bonded surface to surface contact type. So first surface to second surface. So this particular contact will be created, contact tool will be created for this contact region. So I'll just right click on it. Before right clicking and going for the particular contact result, the major important thing is meshing. So whenever you want to figure out the particular like verify like whenever you want to verify your particular contact that you are using for the simulation, like this bonded contact type, you first of all need to particularly generate a better quality of mesh on the geometry, and then only you should go for the particular contact region to be like verified. So if I would go with the default value over here, you can see why did I mention a better quality of mesh. Because if you are going with a particular default kind of mesh over here, you can see the particular gap has been increased a lot between these two bodies over here due to the kind of mesh that has been generated. So this is a particular irregular kind of mesh that you have generated, which doesn't even acquires the particular curvature in the particular model. As you can see, this curvature has not been properly acquired by this mesh that we have created on the geometry. And due to that particular reason, if I would go to the contact tool and generate initial contact results for the geometry over here, so this won't take much amount of time, but just don't know why is it taking a little bit of more time. So if I would go to the initial information over here, you can see both the kind of contacts that we have defined over here. The status of this particular bonded contact type is supposed to be always closed, and that is closed. And over here, you can see the particular gap between both the bodies is mentioned over here. The actual gap between the particular bodies is little bit high. There is a particular pinball region that has been created. What is this pinball region basically? So pinball region is a particular tolerance kind of ball that has been created over here, a sphere that has been created over here. Within that particular sphere, if both the contacts are available within that particular sphere, then the connection will be considered to be a better kind of connection. Over here, you can see the gap has been considered to be very least. So you can see it is not particularly recognizing what is the actual gap between the body. It is just considering this pinball region which is mentioned over here and considering this particular contact to be the considerable kind of contact without considering the actual gap between the body, which particularly should show us some kind of irregularity if we are using a bonded kind of contact type. Because you can see the red color region should be highlighted over here to this contact type because the contact status is open, but the type of contact is meant to be closed. So basically the kind of contact that we are using over here, the contact status is showed to be closed over here. But instead we know there is a gap between the bodies. So that means the status should be open over here at the initial. So basically this particular thing is the irregularity that has been shown over here. As of now, it is not showing you any kind of irregularity. None of the particular contact is highlighted in red color. The reason behind it is this pinball region that has been created. And this pinball region is created because of this automatic contact region, that is this tolerance value. So if I would go to this bonded contact type, and if I would go to this particular pinball region which is been program controlled, if I would click on the radius over here and define a very small radius, that is 0.005. So you can see if I would mention it to be 0.005, somewhere over here it might create a particular pinball region over here, as you can see. Now both the contacts are not available in this particular pinball region which has been created over here. And now if I would go to the contact tool which is present and generate the contact results over here. So you can see the initial information now. Now, as soon as I reduce the particular pinball region, that is from 0.14 somewhat whatever value that was mentioned from the automatic. So I did reduce the pinball region. Now the actual particular status of this particular geometry is far open. And if it is open, and still we are using a bonded kind of contact type. So bonded kind of contact type or the red color highlighted region does defines the same thing. The contact status is open, but the type of contact is meant to be closed. That means the type of contact that you are using. So it is only used when the body's status is closed. So basically it is showing us far open over here. And if we are using the particular contact status that is which is supposed to be meant to be closed, but you are using it for the open status, then the particular contact can't be used for the simulation. So this applies to bonded and no separation contact type. So basically this red color line will be only showcased to this particular bonded and no separation kind of contact type. Because if you are using frictionless, frictional or rough kind of contact type, there is gap that is allowed and the bodies can be connected with each other. So there is no issue with using non-linear kind of contact type. You can use them whenever you want. But if you're using bonded and no separation kind of contact type, there should be no gap between the bodies. The status should not be open at that time. So if that's the situation, the contact status is open. So basically, if it shows you yellow color, that does defines the contact status is open. This may be acceptable. So that's the particular region that is being highlighted over here. Then the third one that is orange. So basically if there is some amount of gap between the bodies, but still if you want to get it connected with each other as we did previously, so using the automatic kind of contact. So it did all automatically took a pinball region through which it did consider both the bodies to be connected with each other. That particular region was previously highlighted with white color, but it was usually supposed to be highlighted with orange color. So it does defines the contact status is closed, but has a large amount of gap or penetration between them. So in that particular situation, your region should be highlighted in orange color. So that means if you're using bonded or like no separation kind of
ಹಲೋ
contact type,
ಹಬ್ಬದ ಹಾರ್ದಿಕ ಶುಭಾಶಯಗಳು. ಹೇಗಿದ್ದೀರಾ?
uh, hello. Okay. So basically over here, as you can see, the contact status is closed. So if you are using bonded or either no separation kind of contact type, and if there is a gap that is present in the body, but if you are providing some kind of pinball region over there to neglect that particular gap, so you can consider your particular region to be highlighted in orange color and you can use your particular contact for the simulation. So that's not an issue, but the result might get a varied little bit with respect to the actual connected body and with respect to a particular body which has gap in between them, but you are considering it to be neglect that gap and consider both the bodies to be connected with each other. So that's a particular designing defect you can consider, but usually the result might also get a little bit varied in such kind of situations. So previously as well, I did a particular session on this particular topic where we did worked on different kind of model. So over here, as of now, we have a gap which is present over there. So if I would change the contact type, that means now you can see we have three different kind of contact type that I can use over here, not the bonded or the no separation, because there is already a gap. If there won't be any particular gap, I could have gone with the particular no separation, because it does allows even sliding between both the bodies. So that would be one of the most considerable kind of contact type. But over here there is a gap, so we need to neglect these two contact type, that is bonded and no separation. The only option that is present over here is frictionless, rough and frictional. So basically if I would go with frictionless, then it will be workful for me, because gaps are allowed between the bodies and sliding is as well allowed. Rough can't be used for the simulation over here, because as you can see, gap is allowed but sliding can't happen between both the bodies. So this is not the particular contact that we need to use. So either we can go with frictionless or frictional, but if we are using frictional, then we need to provide some kind of frictional coefficient as well. So basically we don't have that particular value, so it will be better if you would go with frictionless. But if you want to try it with frictional as well, you can go with that particular values. So as of now, so I'll define this particular contact type to be frictionless. So over here, if as you can see, we didn't change the mesh and anything. So there is still a gap which is present over here. For the frictionless, there is still a small amount of pinball radius itself. So if I would go to the contact tool and generate the initial contact result for this geometry over here. So this will particularly highlight your contact tool by yellow color. So yellow color does defines the contact status is open, but this may be acceptable because the kind of contact type that you have used over here for this contact region is a non-linear kind of contact type, which allows the particular status to be far open from each other. So basically, this is how you need to particularly choose your contacts that you are using for the simulation. You need whatever kind of contact that you will create. As of now, there was just a single contact which was present in over here. But when it comes to multiple contacts, there will be much amount of irregularities between the contacts that you are creating. So you need to be more precise whenever you are creating these contacts. So always try to do this technical verification so that you won't face any kind of issue related to your contacts in the particular solution. So first of all, we need to do the mesh now. So once the contact is being set between the bodies, we need to go for the meshing. So to generate the mesh between both the bodies, what we'll do over here is we need to define an element size. So to define an element size which will work better for our particular model, I'll just define it to be 0.2 over here, or either I'll define it to be 0.3 over here and generate the mesh. So once it is generated, you can see it has now little bit acquired the actual shape of the particular geometry. Still there is some amount of defeaturing. As you can see over here, the actual region is present over here, but the element that has been created is at this particular region over here. That's usually a particular defeaturing itself that usually does happens between the bodies whenever you are trying to generate the mesh. So that's why FEA is considered to be a particular approximate kind of numerical method, not an exact value providing numerical method. So basically over here, we have developed a element size of 0.3. In this contact, whatever the particular regions that we have selected, these two particular regions. But in future, whatever these particular two regions that has been already been selected, not just this, but even more number of edges or faces of the bodies might come into contact with each other. If you would see the particular animation, this upper body is getting in contact with the lower body, and most of these regions of the upper bodies are getting in contact with the lower body. So if you know your particular model in more better way, you can particularly increase your contact regions over here so that you can avoid penetration between the geometries. So this selection of contact region will always help you in particularly maintaining the penetration to not happen between the geometry, to preventing your model from getting penetrated between each other. So this is one precaution that you can take to avoid penetration. The second precaution that you can take is generate more finer mesh on these particular edges which are going to slide over each other, which might actually come into contact with each other. So generate more finer mesh over there. And the third precaution that you can take to avoid the penetration between both the bodies is you need to apply the load in smaller number of divisions so that the solver won't face much amount of issues to particularly apply the load on this particular geometry. So over here for the meshing, to generate more finer mesh to wherever the particular body is been in contact with each other, we'll apply some amount of refinement to those. So I'll just select this particular edges where we want to apply the refinement on. So this particular edges, not this one. So this particular 10 number of edges that we did selected for contact region, on those itself we will apply the refinement as well. So I'll mention the refinement to level 2 and generate the mesh over here. Okay. So once this is done, now my meshing has been improved in near to the particular area wherever the particular bodies might come into contact with each other most of the time. So once this is done, we'll go to the static structural over here to apply the conditions on the geometry to keep the bottom model fixed. So I'll just apply a fixed support over here on the bottom edge of the geometry to make the model not to move in this particular y direction and slide on this particular another body itself. I need to apply some kind of support on this particular geometry as well, so that this particular body should not move in this particular y direction. So there is a particular condition that you can apply, that is either you can apply displacement over here so that you can just consider the motion to be provided to be free in x direction itself, which is your particular vertical direction, so that sliding can happen, and y and z direction to be 0. But instead of that, there is a better support that you can provide, that is frictionless support. So this particular support does only allows motion in the particular planar direction and not in the particular normal direction. So if I would select this particular frictionless support and select these two edges which are present over here, so the body can only move in this particular planar direction itself of whatever plane that I have selected over here, and not in the another direction that we have with us. So why did I mention the planar direction to be this particular vertical x and z direction, xz plane to be the planar direction? Because the thickness is in this particular xy plane, xz plane itself. So whatever edge that we did selected over here was on this xz plane. So the normal is your y direction. So over here you have provided the thickness to the geometry. So that's why you have your particular region uh, where you can define this frictionless support on, and you can particularly recognize your model as well. So if it doesn't behaves in a proper way, you can change it from frictionless to displacement as well. Now after that, I want to move this particular model in the downward direction so that both the bodies can particularly the upper body can slide on the lower body, and the deformation might happen, and the upper body should snip into this lower body and come back again to its original position. So that means we need to do this simulation into two parts. So first will be the upper body should go in the downward direction, and again it should come back to its original position from the downward location. So to do that particular thing, we'll select this top edge to apply the displacement on. The displacement should be applied in the x direction. So I'll mention the value that I have for this, that is 18.551 mm over here. So that particular direction is being showcased in the positive direction. So I need to mention it to be negative 18. So now the model is going to move in the downward direction over here. But once it reaches to the downward direction, it should come back to its original position. So the time step that it takes from this particular location to reach the bottom position is 1 second. So I need to increase the particular time step over here. So the number of steps to the present, I'll mention it to be increased to 2 steps. So the first step ends at 1 second, and the second step which is present over here ends at 2 seconds. So now my simulation is divided into two parts. One is from 0 to 1 and another one is 1 to 2. So from 0 to 1, it reaches to negative 18.51 mm. And from there, I need to make it back to its original position, that is 0. So once it is done, you can see this particular graph represents the actual motion of your geometry over here. Now, once this is done, we'll go to the analysis setting over here. So we did set up the number of steps, the particular time steps and all other things. We need to turn on the last deflection over here, which is the second type of nonlinearity, that is geometric nonlinearity. Basically, why we need to turn this on is the overall body is undergoing the deformation, and the actual deformation that we have provided to the body is very high if we compare it with its length or either whatever the particular dimensions of the geometry are. So that's why we need to turn it on. So we would get more feasible and more better kind of results for our simulation. So after this, so we need to particularly divide the load into smaller number of parts. So that is done through the auto time stepping. Usually auto time stepping does defines that the load will be divided by the solver itself based on the particular simulation. So if I would just solve this particular simulation to figure out what is the amount of deformation that the body is undergoing and try to solve this particular simulation over here, I can have solution information as well as force convergence or either displacement convergence because I have applied displacement over here. You can see the contact status has experienced an abrupt change over here. So that means this contact status has experienced an abrupt change that defines the contact status has got changed a little bit. So contact status change, that means from open status, it has changed to a closed status. So basically there was a gap between both the geometries over here. So that particular gap has been totally been reduced and both the bodies might get into contact with each other. So that particular contact state has been generated over here. And that's what is mentioned in this particular warning message. That does defines both the bodies are behaving as per whatever our requirement was there. So if I would showcase you the result that we are getting from this simulation over here. So if I would play the animation over here, you can see the body is penetrating between each other. Once it reaches to the second step, it come back to its original position, but with respect to the same penetration itself. This defines basically the penetration is being generated between both the bodies. Both the bodies are not behaving as a particular separate body, and both the bodies are not sliding over each other, the condition that we were trying to provide between them. So this is because of the number of load division that this particular simulation is doing over here. You can see the particular time division, that is from 0 to 1 second, it didn't took any particular division of the load. That means it directly did apply a particular load of 18.51 mm on the particular geometry. So that's a irregular kind of division that has been applied, and due to which your particular body is not behaving like the actual body should behave. So what we can do over here is we need to change this auto time stepping from program control to on. Over here, we want to particularly divide the time step. So basically we have 1 second of time where in 1 second it was applying 18.51 mm of particular displacement. So we need to divide that particular displacement into smaller number of parts. So if I would divide that particular division into 100 number of time, then the initial time step will be 0.01, minimum as well I'll mention it to be 0.01, and maximum itself 0.01. So this was for first time step, that is from 0 to 1 second. Now for the second, that is 1 to 2 second, we need to do the same kind of thing. So over here we'll turn it once again to be on, sub step to time step. So there is one more option which is present over here, that is carry over time step. So basically where we did left out from 0 to 1, whether we want to carry from that point itself or either I want to go from the initial once again to do the calculations for this second time step. So it's been asking that particular thing, but we want our particular model to be like pulled back from the particular bottom location. So we need to continue from the particular 1 second location itself. So we'll use this carryover time step to be on, and then the minimum to be the same division of load by 100 times. So we'll check whether this condition will work for our particular model or not. So if I would just solve this particular simulation once again, you can see now how the incrementation of your particular load will be done in your model. So the warning has again occurred over here. That just defines the context status has got changed a little bit. Now you can see the particular incrementation in the time step that is not being directly jumped from 0 to 1. It is increasing in a particular linear manner over here. So this might take a little bit of time. Okay. Yeah. Okay, I'll just keep it program controlled itself. That doesn't matter a lot. Over here in the analysis time step itself, I need to change once again a little bit less number of divisions I need to make, I guess, though. 0.005. This as well, 0.005. Okay. So I'll just go to the solve once again. This might usually take a little bit of time to solve the particular simulation, but if I want to see the behavior of this particular model with respect to the running calculations to be on, so you can see how the model will undergo the sliding over here. So now you can see there is sliding that is being generated between the geometries over here. If I would make it to no frame, so you can see now the sliding is being happened in between both the bodies over here without any kind of penetration. So the major important parameters which affects your particular geometry to lead into particular penetrations and all, those are first your contact regions, the second is your mesh, and the third one is your load division. So load division is done in the analysis setting through the auto time stepping to be changed. So this way you can particularly apply the conditions on the geometry. That is the contact non-linearity can be applied over here. So there are multiple kind of situations where you can use the non-linear kind of contacts. So most of the contacts are considered to be non-linear itself, but you need to know how to particularly define those and how to particularly verify those conditions will work for your model or not. So this way you can solve your simulations over here related to your particular non-linearity of this particular contact simulations. So as of now, I'll just close this particular window over here and I'll just showcase you what kind of result we might get from this particular simulation. Uh, just a second. So if I would play the result directly over here, you can figure out what kind of result that it will showcase to us. So basically this way the model will behave and then come back to its original position with respect to the loads and contact that we have applied between the geometries. So based on your meshing and all, It might take a little bit more amount of time as well. So I'll just stop this simulation because we don't have much amount of time to run the particular calculations as well. So I'll just close this particular screen. Now, to particularly model the joints that we are going to use for the simulation, I'll just go to the workbench screen once again over here. In this particular workbench screen, I'll first of all make use of the rigid dynamic tool. So I'll just drag and drop this rigid dynamic tool over here, where I don't have to focus much on the engineering data. Rigid dynamic itself does defines the particular overall simulation model that the overall model that you will be using for the simulation will be a particular rigid bodies, the particular body that you will be using for the simulation will be totally consisting of rigid body parts itself. The behavior of the all the bodies will be totally rigid. So if bodies are rigid, then there will be no deformations or stresses generated on the body. So we don't have to much focus on the engineering data over here. So whatever materials those are being used over here, just the density property will be considered for the simulation if all the bodies are considered to be rigid. So over here in the geometry, I'll just import a particular geometry where I can showcase you how to particularly generate automatic joints as well and manual joints as well. So those kind of things we'll try to recognize over here. So instead of a particular excavator arm, I'll use particularly uh, V6 model itself. So a 6-cylinder model over here. So whatever this particular geometry that I have with me, I'll just open it in SpaceClaim to just showcase you what kind of model it does look like and how to particularly create automatic kind of connections, uh, connections in the sense automatic kind of joints between the geometry that we have imported. Uh, I'll try to showcase you how it is done in SpaceClaim as well, how the particular procedure is being followed to generate automatic kind of connections from SpaceClaim itself, and even how we can generate automatic connections in Ansys Mechanical itself. So we'll look out into those things over here. So first of all, we have a geometry like this, that is this particular piston body that we are going to use for the simulation, where there are 6 number of piston heads, those are available, 6 number of gudgeon pins which are available. Those are connecting your piston head with the connecting rod. Then this connecting rod is also in contact with the crankshaft which is present over here. So basically all these bodies which are present over here will be contact with each other. So the joints will be created between that particular point where both the bodies are sharing a single axis for rotation or for particular motion. So that particular region you should figure out and you should create a particular joint over there itself. So whatever the particular geometry that we have with us, either we can create a groups. So basically automatic some groups has been already been created, not automatically. Previously it was being created already. So I'll just delete all those groups which are present over here. So whenever you want to use this particular simulation, this particular geometry for the joint modeling. So if you want to create automatic joint, you should create some kind of group between the bodies between which you want to create the joint, and then go for the particular automatic joint creation. Instead of this, I'll also let you know how this same procedure can be done in Ansys Mechanical as well. It will be more feasible for you to understand instead of this particular space claim screen. So I'll just minimize this particular geometry over here and I'll go to the Ansys Mechanical to open this particular model over there. Okay. So the overall model has been imported over here. This particular V6 model. So as I did mention, we can create automatic contacts and automatic joints for this particular geometry. Before that, I want to showcase you how the particular behavior of the body is set at the initial. So based on the kind of solver that you will be using for this rigid body dynamic simulation. So the solver that is mentioned over here is a RBD solver itself, that is rigid body dynamic solver. So this particular rigid body dynamic solver the sets all your particular geometries which you will be using for the simulation to be rigid itself. So if I would click on any of the geometry, you can see the stiffness behavior of the geometry set to be rigid. And if it is set to be rigid, then there will be a particular coordinate system that will be created at the center of gravity of this particular geometry. If I would hide all other bodies which are present over here, you can see the coordinate system that has been created for this particular geometry is created at its center of gravity over here. So that particular inertial coordinate system will be considered to particularly recognize the motion between the bodies. So rigid bodies are only used at the particular time when they are considered to be a kind of rigid bodies itself. Those will not undergo any kind of deformations or stresses, or either if you want to just use them for rigid dynamic or rigid kinematic kind of simulations. So over here, if I would click on the crankshaft body, if I would change its stiffness behavior from rigid to flexible, this particular body will not have any coordinate system with it, and I can even generate mesh on this particular geometry now. So basically, when it comes to rigid bodies, we are not focusing much on the particular deformation of the geometry or the stresses of the geometry. So if we are not interested in finding out the stresses and deformations on rigid bodies, then particularly there will be no requirement of the mesh itself. So rigid bodies doesn't allows you to generate any kind of mesh on them. But if it is a flexible bodies, you will always create mesh on your particular flexible bodies over here. So we don't want this to be flexible. We'll keep it rigid as it is. So show all bodies. So once this is done, so as you can see, the next thing that we have over here is the connections. So basically automatic 24 connections has been created between the geometry over here. So these all are the contact region, not the joints that we wanted to create. So basically, as you can see over here, all the bodies have 24 number of different contacts those have been created over here. So usually this is considered to be not used for the particular kinematic simulation, because contacts are not required to particularly provide motion between two bodies. So that's why we don't need this contact region. If automatically contacts have been created and you are using totally a particular rigid body combination over here, still the mesh will be created only on the only on the particular rigid surfaces wherever the contact regions have been created. So if I would just showcase you this particular thing, if I would just go to the mesh and generate the mesh on the geometry, it won't take much amount of time to generate the mesh for this overall body combination that we have. Over here, some of the entities got filled, but on some of the entities, it might have generated the mesh. So as you can see, not on the overall geometries, because all the geometries have been considered to be rigid, but wherever we have created the contact regions, on those surfaces itself, it has created some kind of mesh, as you can see over here. So basically, wherever the bodies are in contact with each other and we have selected some of the surfaces to be in contact with them, so there itself, the contact has been created. If I would hide this body, you can see mesh has been created somewhere over here as well, somewhere over here. So wherever those are connection between the geometries over there itself, it is creating this particular mesh. So if I would just showcase all the geometries, as you can see, these contacts are not usually required for kinematic simulation. So we are going to delete these contact regions those have been created over here. So there is a particular use of contact as well when it comes to rigid body dynamic simulations, that is kinematic simulations as well. So contacts are different kind of things during the kinematic simulations, and how they are used is a different method. So over here, we want to go for particular automatic connections and even manual connection. Now, if I want to provide motion to this particular V6 body which is present over here, what I'll do is I'll provide some kind of motion to this crankshaft. The motion from crankshaft will be provided to your connecting rods, and from connecting rod it will be transferred to your gudgeon pins, and from gudgeon pins it will be transferred to your piston head. And with respect to your connect crankshaft, so this piston head will also be rotating over here. So we don't want it to provide some kind of rotation. We want it to reciprocate in the particular translational direction. So how to provide all these particular motions to your geometry over here? So what we'll do is we'll first of all look out how to particularly create an like manual joint over here. So if I would right click on the connections, I can create a joint over here because all the bodies are rigid. So we don't have much different kind of connections. Those are available. So if I would click on joint over here, I can first of all select the region of the crankshaft where I want to provide the rotational motion over here. So if you would want to provide rotational motion to crankshaft, so we don't have any particular external body to provide the motion. So we'll connect this particular crankshaft with the ground body so that from ground there is some kind of external force which is rotating this particular crankshaft. So the contact type, connection type that we will select for this crankshaft is body to ground. So whenever motion is being provided from some external body to your particular initial rotation or either some kind of particular constraint that you want to give to the geometry, then you need to connect your body to the ground. So once your body is connected with the ground, you just have to select the mobile body, not the reference body. So whenever we were trying to create contacts between the bodies, usually we were selecting contact and target regions over there. So in similar way, whenever we create joints, we select references and mobiles. So reference body is a body which provides the motion to the geometry, and mobile body is the body which undergoes motion due to the reference body. So over here, reference body is your ground body, which provides the motion, but which is not available with us. So it will automatically be considered as ground itself. So we don't have to make any selection over there. But mobile body over here is your crankshaft, which is rotating due to your external force that is ground. So we need to apply this particular selection of this crankshaft over here in the mobile body. So now your mobile body, that is this crankshaft, will undergo motion due to the reference body, which is ground. So that's why it has been grayed out over here. That represents your reference body is a ground body. So the type of joint that you have to use over here, as you can see, there are many number of joint types. Those are available like revolute, cylindrical, translational, and all other types. So from these all types, which particular type of connection that you should use for your particular joint depends on what kind of motion that you are trying to provide. So we want to rotate this crankshaft. So rotation can be provided through revolute. So as you can see, only the rotation about Z axis is available to be free over here. All other directions are supposed to be fixed itself. So that does represents this rotation about Z is only free. If you would go to this particular coordinate system, as it was already mentioned, each joint has its own coordinate system, which is present over here. You can see the Z direction is in this particular direction, in this particular uh, direction over here. So the rotation to this crankshaft will be provided around about this particular Z axis. So if I would go to the revolute, go to joint over here and try to configure and try to rotate this particular geometry, you can see the geometry will undergo the rotation over here. So this was the joint that I was trying to provide it over here for this particular model. And this way you can create your particular body to ground joint. In the similar way, if you want to provide body to body joint as well, so I'll just showcase you that in the further particular connections that I'll make. But first of all, we'll go for automatic connections. So automatic connections you can create, but for that you need to create group between the bodies over here. So how we are going to create the group between the bodies that we didn't create using the space claim screen. So to create those, I'll just click on the body selector over here. So whenever you want to create joint, you should select bodies. So bodies which are in contact with each other. So crankshaft is in contact with these all connecting rods which are present over here. So if I would select all these connecting rods which are in contact with each other, so these contact regions, this particular crankshaft is connected with connecting rod. So I'll just create name selection for them to create as a group of these particular bodies. So if I would click on create name selection and name it as group 1, GR1, and enter. So you can see in the name selection, there is a group that has been created for this all geometries over here. Now these connecting rods are in contact with your particular piston head, these gudgeon pins as well. But before that, if I would right click and click on inverse visibility. So where is that option to click on? Okay, so I'll just click on hide body. So you can see these piston heads are connected with your gudgeon pins which are present over here. So if I would select all these bodies which are present over here, I'll just click on select all and then click on right click and create a name selection for this particular bodies as well. So name it as GR2. So this was second combination. This was the first combination. And if I would showcase all the bodies over here, the left out are just this connecting rod and the gudgeon pins. So basically I need to use this particular combination over here. So what I'll do is I'll click on this apply. Okay. Instead, I'll just select one by one all the bodies which are present over here. So first of all, the connecting rods which are present over here. And then the gudgeon pins which are present inside these piston heads. Once all these have been selected over here, I'll just right click on it and click on hide all other bodies. So now just the connecting rod and the piston head, connecting rod and the gudgeon pins are available over here. I'll just right click and create name selection for all this by selecting all. I'll create a group of this one as well. So GR3. So group for all these three have been created over here. Once you create a group for all these three bodies which are in contact with each other, you can create the particular automatic joints for these particular geometries over here. So to create automatic joints and contact, we need to create a connection group over here. So I'll click on connection group. The connection type that I want to create is not contact. I want to create joints over here. So joints should be created, but for what bodies I want to create the joints. So I want to create for name selection that I have made over here. So first I want to go for GR1, that is crankshaft and connecting rod. So this name selection can create two different kind of joint. One is either fixed or either revolute. So I want rotational joint because this crankshaft is rotating, and with respect to this connecting rod will also be rotating. So I don't want fixed joints over here. I want just revolute joints. So I'll just do that particular selection and right click on the connection group and click on create automatic connection. So you can see automatically 5 number of joints have been created. I'll click on rename based on definition over here. So all the joints between the crankshaft and the connecting rod will be created over here. So once this is done, in a similar way, I'll create similar kind of joints using automatic kind of contact for the second group as well and create it. So the third one as well, using the same kind of connection group, using the joints name selection, GR3. No fixed joints, only revolute. So I'll just right click on it and create automatic connection. Now I have created all the number of joints that I wanted for my particular simulation over here. So I'll just right click on it and rename based on definition. Right click on it, rename based on definition. So you can see the naming of these particular joints as well over here. All of them are the revolute, but I have some of the joints which are still left out to be provided over here. Now between all the bodies, the joints have been created properly. Just left out regions are your particular piston heads where you want to particularly provide reciprocating motion and not rotational motion. Because if I would go to the revolute, first one, and try to rotate this particular geometry, you can see the overall body is getting rotated with respect to it. So the piston head should undergo reciprocating motion, which will give me a particular motion of the combustion over here. That means the actual V6 motion. So over here, I'll go to the connections. I want to create a joint. So that particular joint should be your body to ground joint once again, because these piston heads are particularly constrained due to the cylinder liners. So those are not available over here. So to constrain its motion to just reciprocating. So we need to connect it with ground. Instead of fixed, we will give it translational motion. So which allows only free motion in the X direction. So now to select the particular face, I'll click on this particular axis, this particular surface over here and apply. Now you can see only the X direction is free to move. So this particular piston head will only undergo motion in this X direction over here. Now in the similar way, I want to create the remaining joints as well. So body to ground, translational joint for this particular face over here. Similarly, body to ground, translational joint for this another face over here, body to ground, translational for this face as well. I'm not creating automatic for this particular region because these all are the particular body to ground kind of contact, and body to ground can't be created with respect to your automatic connection type. So this way you are done with particularly creating all the number of joints that you wanted to create for your particular geometry. Once this is done, if I would go to the mesh now and generate the mesh, there will be no mesh that will be available for your geometry because there are no contacts as well and no flexible bodies which are present over here. Once this is done, you can provide joint conditions to make your body rotate. So the actual rotation was going to be provided due to this crankshaft. So we'll use that particular joint itself. So I'll create a joint load over here. In that joint load, I'll use the first joint that I did created for this crankshaft to rotate. So you can see the arrow that has been showcased over here does represents only rotational forces can be provided. So the only degree of freedom that is free to rotate is rotation about Z axis over here. In the type that we have, I'll select either rotation, rotational velocity, rotational acceleration or movement, but I want to apply rotational velocity. And in this rotational velocity, either you can apply the magnitude in terms of RPM or either you can apply it in terms of rad per second. So we'll go with RPM itself. So at zero velocity, at zero time, we have the RPM to be zero, and at 1 second, we will make it as 500 RPM over here. So you can see how the variation from 0 to 1 second is being done over here in terms of RPM that we are providing to this particular geometry. Once this condition is provided, there are no requirement to provide the particular conditions to your geometry over here. So there is no particular requirement to do the redundancy analysis as well for this particular geometry. But still, if you want to do, you can just right click on the connections and click on the redundancy analysis. This kind of worksheet will be opened in front of you where you can click on the generate option to analyze it. So it will showcase you some of the faces which might show some kind of problem to you. These are the faces which are redundant. That means they can undergo motion in some another direction if provided. But rather than that, there is no particular issue in our overall geometry over here. So how we will recognize that? That too we can recognize with the solution that we will get from the simulation. So if I would go to the solution result, add deformation. So deformation, as I did mention, we can't find out for rigid bodies, but this deformation is the motion deformation and not the body deformation. So basically, whatever the motion, that means the position of body does changes from its initial location, that total deformation is calculated over here and not the actual body's deflection. So over here, uh, the next thing that was left out is analysis setting. Over here, as you can see, this is particularly a non-linear kind of simulation itself, because this is a particular dynamic kind of modeling that we are using, and auto time stepping has already been set with minimum time step to be very less and maximum as well to be a little bit high. And you can see all these results have already been set over here. So if I would go to this particular solution and solve it, it won't take much amount of time. The reason behind this is there are very less number of degrees of freedoms those are available on the model. And the reason behind it is there is no mesh that we have generated on the geometry. And you can see the solution got solved very quickly. So if I would just showcase you the result for this particular simulation, I can run this particular model over here and you can see the motion of this particular geometry behaving as a particular V6 engine itself. The reciprocating motion of your particular piston head on all other bodies to undergo just the rotational motion itself. So this way you can particularly use the joint modeling method for your particular joint creation and the contacts that we did created for non-linear contact kind of simulations. So that was all the post processing and the analyzing of your particular result. In this solution information, you can even analyze the energy graph as well, how the potential energy and the kinetic energy in your particular model does behaves with respect to whatever the total energy that has been generated in the model. So that's all for this particular session. Anyone if wants to ask or has any kind of doubt, please let me know.
Chetan, there are some questions in the chat box.
Yeah, I'm going through them.
Yeah. They want to know some time steps again. Yes.
Yeah, Shivam, I'll share you the model as well. So with respect to this particular recording of the session, we'll try to share the PPT as well and even the model that we have used for this particular simulation. Okay, so time step. Yeah, okay. So basically, time step is one thing that we usually use whenever we want to make the division of the particular load that you are applying. So if I'm applying a particular load of consider 100 Newton on my particular geometry over here, and usually that particular load that I'm applying on the particular geometry is considered to be applied from 0 to 1 second. You can decide you whatever particular end time will be there. It does depends on you what particular end time that you will be using for your simulation. So if I'm using my particular load to be applied as 100 Newton within 0 to 1 second, but actual solver is not capable of solving overall load at a single go itself. So you need to make smaller number of divisions of the load that you are applying so that the solver will be capable of applying the load in a particular feasible way and even there won't be any particular irregularities. Uh, Okay, I'll just let you know how to overcome the particular errors in over constraint kind of models. But let me just complete this auto time stepping over here. So basically, whenever you want to make the divisions of whatever the load that you have applied, so you have two different method. Either you can go with the auto time stepping. That means some automatic variation will be done with respect to whatever the values that you will mention over here. And the another method is you can just directly turn it off, which will help you in directly defining how many number of actual divisions that you want in your particular body to make. So those two things are available that can be done. Basically, auto time stepping is one thing where you divide your particular load using three different parameters. One is initial time step, then minimum time step, and the maximum time step. Initial time step does only decides from where your simulation should start. Minimum and maximum are two parameters from where your particular another value of your simulation will be selected. That means the incrementation of the load will be selected between those two values over there. So that's a little bit tricky kind of thing. To explain it in more detail, I'll try to share some kind of contents as well. You just try to reach me out on the mail ID I'll just mention over here. I'll try to share some kind of contents related to it with you. Okay. So yeah, Amit, how to overcome the error report over constraint. So basically, whenever you do the redundancy analysis, right? So as you can see, if I would go to the redundancy analysis over here, if I would click on the generate option, so it will automatically highlight some of the regions which are in yellow colored. So if it shows you yellow colored, basically you can directly change the type. So if it is showing you the redundant faces or redundant directions over here, so you can change it from free to fixed. So if you would try to free or fix some of the directions from your particular joint, the type of the joint might get changed over here. So this particular thing does defines the rotation about Z direction is only free with respect to the type of joint that you are using. But even the motion can be generated in X, in Z direction as well, and in rotation about X and Y as well. So this does defines the particular redundancy is due to another joints that you have created with reference to your particular this joint. So what you can do, another thing over here is you can particularly change the displacement directly over here, or the particular thing to overcome this kind of errors over here is you can just do configure your particular model. So if I would just generate it 1 second over here, if I would go to the revolute, click on okay, just a second. I guess my screen is not visible. I hope it might be visible now. So over here, in this particular redundancy, as you can see, there are multiple redundant regions which are present, the directions which are present. These redundant directions are due to another joint that you have created in reference to this particular joint that is been having some redundancy over here. So this doesn't represent some kind of irregularity. But if you want to still particular overcome this particular redundant faces, so this can't be totally removed from your particular joint that you have created. But if there is any kind of error that you are facing with respect to your model, what you can do is you can just click on any of the particular joint that you have created, and to know whether it is working properly with respect to the joints that you have created in further or in previous connections with respect to the joint. Like as you can see, before I did created this particular joint, I did created some joints for the gudgeon pin and the piston as well, and this piston to ground to piston as well. So that means the body, if I would just give some reference, it would be more better. So if I would select this connecting rod, this connecting rod is connected with the crankshaft as well and with the gudgeon pin as well. So if I'm trying to provide some kind of different motion to gudgeon pin, which is not capable for this connecting rod to undergo, because I did connected this connecting rod with the gudgeon pin as well. So if I'm trying to provide it some different kind of motion, the connecting rod would also undergo different kind of motion. And it is not possible to undergo different kind of motion to connecting rod because its motion with gudgeon pin has been already been constrained over there as a rotating kind of motion. So that's why this particular redundancy does occurs. And to particularly overcome such kind of errors, if there are some kind of over constraints in your geometry or under constraints in your geometry, what you can do is you can just click on any of the joint that you want to change it. So that you want to analyze, first of all, you can just go to the joint and click on the configure tool over here. Once you click on the configure, it will try to particularly show whether the body is able to move, the joint is able to move or not. So if it is able to rotate, it doesn't show any kind of configuration error at that time. That means your particular joint is correct and you can move further for your particular simulation. But if it shows some kind of messages like failed to configure, like I'll just showcase you one particular thing by changing it over here. I'll change the revolute joint to fixed over here. And if I would go to this particular revolute motion and try to configure this now, if I would try to rotate, as you can see, it is showing me a particular method that is failed to configure. If I would go now to the connections over here and try to do the redundancy analysis and generate the result, so there might be some particular regions. Uh, where is the particular thing? Okay, so this one. So basically, as you can see, this particular crankshaft is totally being fixed over here in all the directions. So what you can do is you can just click on this particular first one, which we have considered to be fixed over here. Click on the configure. If it is not able to configure, that means there are no degrees of freedoms which are available. If I would go to the second one, and if I would check to configure it, basically redundancy, we are on the redundancy analysis over here. Okay, so if I would just go to the fixed one, and as you can see, I'm not able to configure this one. If I would come to the another one, I'm able to particularly move this particular joint which is present over here. Okay, so this one is also not rotating. Okay, as I did mention already, basically this particular connecting rod is in contact with this crankshaft as well. And this crankshaft itself is in contact with the another tools which are present over here. So that's why the total motion of this particular geometry has been constrained due to just a single constraint that we have applied over here. So to overcome this, the only method which is available is you can just check whether you are able to configure it or not. If you are not able to configure it, if it is showing you some kind of configuration error, then you can just go to the another contacts that joints that you have created for the particular geometry, and you can check their particular coordinate system that you have used. The only method that you can face the errors with respect to the joints that you have created is either the type of the particular joint that you have selected or the degree of freedom, that is the particular reference coordinate system. So these two are the only things that might affect your particular. Yeah, you can extract the forces as well. So if you would just right click on the forces that you have with you, actually my screen got lagged a little bit over here. Don't know what happened with the screen. So you can just right click on the particular any one of the joint that you have created. You can drag and drop it into the particular solution, and you can just create the force reactions on that particular joint. Yeah, actually my screen got freezed a little bit, so I'm not able to share my screen as of now. I'll try to share the same kind of model with you all as well, so you can practice on it. And if you face any kind of issues, you can just reach me out to whatever the mail ID that I did shared with you in the chat box.